Hello, everybody. Today we will be discussing on the topic understanding the structure of atom regarding introduction to atomic structure. The atomic structure is the foundation of chemistry, explaining the behavior of matter and its interaction between the atoms. This presentation will cover key concepts such as discovery of subatomic particles, atomic models, the dual nature of matter, and the principles governing electronic configuration. The milestone in identifying the fundamental particle of atom and the contribution to the atomic structure, the major contribution by Sir J.J. Thomson, Rutherford, and Chadwick will be discussed. Sir J.J. Thomson discovered the electron through cathode ray experiments, proposing the plum pudding model. Rutherford identified the nucleus in the proton through his gold foil experiment, whereas Chadwick discovered the neutron, completing the understanding of atom structure. The atomic numbers, isotopes, and isobars will be discussed. The atomic number is the identity of an element. It corresponds to the number of protons found in the nucleus. It determines the element's position in periodic table and its chemical properties. Isotopes are different forms of same element that have same number of protons but different number of neutrons. This variation can affect the stability and radioactivity properties of the element. Isobars are atoms of different chemical elements that have same mass number. Despite having the same mass number, the isobars can exhibit different chemical behaviors. Going to the Thomson's model of atom. Thomson's model proposed that atom is composed of uniform sphere of positive charge with negatively charged electrons embedded within. This model aimed to explain the distribution of charge within the atom and a significant step towards understanding the atomic structure. The Thomson's model was unable to explain different properties. It was unable to explain the atomic structure. It neglected the electron behavior dynamics. It does not account for the explanation of existence of isotopes. So, Rutherford proposed a model. And according to him, the atom consists of a dense, positively charged nucleus surrounded by electrons, resembling a solar system. This model challenged previous theories by suggesting that atoms are almost mostly consists of an empty space. Limitations of Rutherford models were also there. It was inadequate in explaining the spectral lines. It failed to describe the electron transition. It does not explain very clearly about the chemical bonding. Hence, Bohr's model was proposed in which electrons move in definite circular orbits around the nucleus, each corresponding to a specific energy level. This model introduced the concept of quantized energy level, where electrons can only occupy certain allowed orbits, leading to emission or absorption of energy as they transit from one orbit to another. Again, there were some limitations of the Bohr model. Bohr model could not explain the other atoms besides hydrogen atom. It was able to explain the spectral behavior of hydrogen atom only. It neglected the electron-electron repulsion. It was inadequate in explaining the spectral behavior of heavier atoms. Hence, on to let us move further and let us discuss the concept of shells and subshells. Shells are designated by a principal quantum number n, which indicate that energy levels of electron. The value of n can be any positive integer, such as 1, 2, 3, which define the shells in the atom around the nucleus. Each shell can hold a maximum of 2 square electrons, provided the framework for understanding how electrons are organized within an atom. Subshells are divisions within each shell. Subshells are classified as S, P, T, and F. The shape and capacity of each subshell varies. Subshell is spherical, P subshell is a double shaped, D subshells have a complex geometry, but each subshell can accommodate a specific number of electrons. For example, S subshell can accommodate 2 electrons, P subshells can accommodate 6 electrons, D can accommodate 10, and F can accommodate 14 electrons. Let us discuss the dual nature. Matter and light display a dual characteristic, behaving both as particle and waves. The duality is fundamental to quantum mechanics, influencing our understanding of atomic and molecular behavior. According to de Broglie's relationship, it is the hypothesis proposed that all matter exhibit wave-like behavior, suggesting that particles such as electron can be described by wave function. This principle forms the foundation of quantum mechanics, bridging the gap between classical and quantum theories. Heisenberg's uncertainty principle asserts that it is impossible to determine both the exact position and momentum of a particle at the same time. This principle highlights a fundamental limit to precision in quantum mechanics, reflecting the inherent uncertainty in the behavior of particles. Let us proceed with the concept of orbitals. Orbitals are fundamental to understanding atomic structure, representing regions where electrons are likely to be found. They are defined by unique shapes and orientations that influence the arrangement of electrons in an atom. The quantum numbers. There are 4 quantum numbers. Let me discuss the principal quantum numbers designated by small n. It indicates the main energy level of an electron in an atom with values that are positive integers such as 1, 2, 3, etc. Higher values correspond to energy levels farther from the nucleus. The angular momentum quantum number L determines the shape of the orbital. It can take on integer values from 0 to n minus 1, corresponding to different types of orbits. For example, the angular momentum quantum number for S orbital will be 0, for P it will be 1, For D, it will be 2, and for F, it will be 3. The magnetic quantum number specifies the orientation of orbitals in space. Its value can range from minus L to plus L, allowing for various orientations of orbitals within a given subshell. The spin quantum number S describes the intrinsic spin of an electron, which can be either plus half or minus half. This property is crucial for determining the electron's magnetic character and its placement in the orbital. The shapes of S, P, and D orbitals. S orbital is spherical, indicating a uniform probability distribution around the nucleus, where electrons are likely to be found. The p orbitals are double shaped, representing two lobes on either side of the nucleus, where probability of finding an electron is highest. The complex shape of d orbitals can include clover-leaf formation, allowing for a variety of orientation and electron configuration. Now, the rules for filling electrons in an orbit. According to Aufbau principle, it states that electrons are added to the lowest energy orbital first, ensuring that each orbital is filled to its maximum capacity before moving to higher energy levels. This principle is fundamental in determining the electronic configuration of an atom and is crucial for understanding chemical properties. The Pauli's exclusion principle. It asserts that no two electrons in the same atom can have identical set of all four quantum numbers. This principle leads to the arrangement of electrons in distinct orbitals, preventing overcrowding in any given orbital and influencing the atom's stability. The Hans rule states that when electrons occupy degenerate orbitals, one electron occupies each orbital singly before any pairing occurs. This minimizes electron electron repulsion, leading to greater stability within the atom's electronic configuration. The Aufbau principle dictates that electrons occupy the lowest energy orbital before filling higher energy levels. This sequential filling process is crucial for determining the electronic configuration of an atom, impacting its chemical properties and reactivity. The Pauli's exclusion principle is a fundamental rule in quantum mechanics, which dictates that each electron in an atom must have a unique set of four quantum numbers. This principle ensures that no two electrons can occupy the same quantum states within an atom, contributing to the structure of atom, contributing to the structure of electron cloud and influencing atomic behavior. Hans' rule states that when electrons occupy orbitals of equal energy, they will fill each orbital singly before pairing up. This minimizes electron repulsion, leading to a more stable electronic configuration. The electronic configuration of atoms. It represents the arrangement of electrons in the energy levels and sublevels of an atom, determined by quantum mechanical principle. According to Aufbau principle, the order of filling orbitals follows the Aufbau principle, where electrons fill the lowest energy level first, followed by higher levels. The Pauli's exclusion principle. It states that no two electrons can have same set of quantum numbers, ensuring unique state for each electron. The Hans rule states that electrons will occupy degenerate orbitals singly before pairing up, minimizing repulsion between electrons in the same sublevel. Now, let us discuss the stability of half filled and completely filled orbitals. Half filled and fully filled orbitals are associated with lower energy states, leading to increased stability at the atom. This stability results from symmetrical distribution of electrons and reduced electron electron repulsion within the orbital. Let me conclude. A summary of essential concepts in atomic structure, including the discovery of subatomic particles, atomic model, quantum mechanics, and the significance of electronic configuration. Understanding these principles is crucial for comprehending the behavior of matter and the fundamental interaction between atoms. That's all for today. Thank you.